Hi, this is a video, just kind of an introduction video to the properties of light. So the question I have for you, and we're going to be answering this throughout this unit, is light a wave or is it particles? And right now we're going to focus on it as being a wave, but in reality there's times where looking at wave characteristics isn't enough for us to understand certain things, and we'll get to that too. So we talked about this briefly in the video where I talked about gamma radiation. The electromagnetic spectrum is, these are all waves traveling at the speed of light, and they have different frequencies and wavelengths. So we have on one end the really big, like these are like between buildings size waves, radio waves, and then we work our way into microwaves. Our cell phones work somewhere in some of those frequencies. Infrared, that's where, like if we have a remote control for, I don't know, I think like my remote control for my smartboard is infrared, I think. Then we have this really small part called visible light. And that's our, if you guys remember I don't know if you know the acronym ROY-G-BIV, and that's for red, orange, yellow, green, blue, indigo, violet. So those are the colors that we're able to see. There's some things like insects and animals that can see into the infrared or the ultraviolet, but we are only able to see in this certain frequency, which we call visible light. And then we get to higher frequency light, ultraviolet, X-rays, and then finally gamma rays. But these are all of these are waves, and they're called electromagnetic radiation. So like I said before, all of these waves travel at the same speed. The speed of light is 3.00 times 10 to the 8th meters per second. So just some properties about waves. I don't know if you know this or not, so we'll just cover it. We have the wavelength, which is the distance between any two corresponding points. A lot of times people go crest to crest or trough to trough, but you could technically pick any two of the same similar point on the next wave. That gives us wavelength. So wavelength is symbolized with the Greek letter lambda. I don't know why they put a cross on that one. It was whatever when I inserted the shape, but anyways, you'll see this Greek letter lambda, and that represents wavelength. The units are any distance units. When we're working, a lot of times it'll be nanometers, and then we'll convert it to meter. But it could be any distance unit. Frequency is how many waves pass per second. So the unit is waves per second, which is also the same as inverse second, and that's also known as a hertz, spelled H-E-R-T-Z. So there's a relationship between, you could see that in the diagram, that as the frequency goes up, the wavelength goes down. So those are inversely proportional or related to one another. And we can use this equation to show that and to also solve for the frequency if I have the wavelength, for example. So this is the speed of light, and that speed of light then equals that wavelength times the frequency, because this is going to be in a unit like meter. This would be in an inverse second. So you'd end up with a speed unit of meters per second. So here's an example calculation. I'm going to let you guys think about what is given and what we're looking for a second. So in the question, they're telling us that the wavelength is 700 nanometers. So I think this was one of them that you saw in the demo that I did, lithium chloride. And then we know the question is asking for frequency. By the way, the frequency, they don't use an F. This is actually a Greek letter called nu. We love Greek letters in science. But anyways, it looks like a V, and I don't care if you write it as a V, but just realize that is frequency. And I probably didn't explain that well in the previous slide. But anyways, so now if I'm trying to solve for frequency, I'm just going to plug in. So I have my speed of light would equal my wavelength. Before I do that, though, I do need to make sure that I have it in meters, because this speed of light is in meters. So I know that there's 10 to the 9th nanometers in 1 meter. Let's give this a sig fig too down there. Let's say it was 700 point. So then when I convert it, I'm going to get 7.00 times 10 to the, 1 second, to the negative 7th, right? Now I don't have a pen. Hold on. So yes, it would convert to 7.00 times 10 to the negative 7th meters. So when you're using the equation, if you use the speed of light in meters per second, the wavelength has to be in meters. So if it's not, then you would want to convert it. So back to the calculation then, let me come back here again. So we know that the speed of light is this, where we know the wavelength is 7 times 10 to the negative 7th. And then we know we're solving for frequency. So I would want to divide both sides. And when I do that, you can see this is meters. The meters cancel and you end up with 1 over second because this would come to the denominator. So frequency is going to equal, now I got to calculate it. So once I divide 3.00 times 10 to the 8th divided by 7.00 times 10 to the negative 7th, I do get the frequency. And it is with 3 sig figs, it would be 4.29 times 10 to the 14th. So it's a high frequency wave in terms of the unit hertz. So that would be inverse seconds or 1 over second or hertz, all the same thing.